Hi again, everyone. So this is the last recording for this week, and the topic is, as you can see, sequential equilibrium. And sequential equilibrium is a refinement of Bayesian-Nash equilibrium, but it's even a refinement of perfect Bayesian equilibrium. And I think that will be our focus. So let's first briefly look at the definition. It's actually very similar to the definition of perfect Bayesian equilibrium. There is something that's called consistency as well and sequential rationality. So we are talking about assessments. There's a sigma, profile of strategies, and beta, a profile of beliefs. So probability distributions over information sets. And well, one of the requirements is exactly the same as for perfect Bayesian equilibrium, namely that given the beliefs beta, sigma is sequentially rational. But the other one is a bit different. So the consistency requirement is what it says here. So if you want to check a sequential, whether sigma beta is sequential, you have to be able to construct a completely mixed sequence sigma k over here. And completely mixed means that every action in every information set is chosen with strictly positive probability. So you do play all your actions with a non-zero probability. And you have to be able to construct a corresponding beta k in such a way that, well, the sequence sigma k converges to sigma, the beta k's converge to beta, and the beliefs are induced by sigma k via Bayesian updating. So in that sense, choosing the beta k is a bit artificial statement, because once the sigma k's are chosen, then from this, it follows that the beta k's can be actually computed, and not just can be computed, but are determined. By Bayes' rule. And you may recall that for perfect Bayesian equilibrium, this was not always true. You could only use Bayes' rule if the probability of reaching an information set was non-zero. That would still be true here, but because the sigma k's are completely mixed, that exactly means that you do reach every information set with strictly positive probability. So this statement over here guarantees that you can always use Bayes' rule, and therefore you should, and therefore the beta k's are always fixed. So basically what you need to do is to compute, to choose this sigma k in such a way that it converges to sigma, and in such a way that the induced beta k's converge to beta. That's basically what it says. So that the existence of this is actually true, but it should automatically follow from Bayesian updating. Okay, so that's the first statement. And the second statement simply says that sigma should be sequentially rational with respect to beta. So that is the same as before. A few remarks. The first one is that, like I said, the sigma k's are completely mixed. So that means that the beta k's are uniquely defined. And therefore, once the sigma k's are chosen, you can no longer choose the beta k's, are simply given by Bayes' rule. And secondly, that is indeed a strong version of consistency, and therefore sequential rationality is indeed a refinement of perfect Bayesian equilibrium, because the sequential rationality condition, the other condition, is the same as for PBE. So it's really a refinement. So that's nice, because that means that if we want to compute sequential equilibrium, if we want to compute all the sequential equilibria in a game, then what you can do is to simply look at the game, first compute the perfect Bayesian equilibria, and then see which ones are of those that you found are sequentially rational. So that is what we're going to do in the example that we have seen before. So this is the game from the previous recording. In this game, we already computed all the perfect Bayesian equilibria. And in this recording, I'm going to take one of the 3 line segments that we found and check for that line segment. Whether or not the equilibria in that line segment are indeed sequentially rational. And I think we're going to look at these over here. And so these are the corresponding beliefs here. So maybe a short remark before we start. It says here that the alpha is between 0.5 and 1. So completely mixed would mean that the alpha case, right? So the sequence that converges to alpha should be strictly between 0 and 1. And that is actually a reason to split this in 2 cases, namely the case where the alpha is strictly smaller than 1. So for any alpha with this, of course, then automatically we have that alpha is already between 0 and 1. So you might try to make this sequence constant, and usually you can. So that's what we're going to do. And then the alpha is equal to 1. That will then be a special case. So you can split all these different equilibria in different cases that you treat differently. Also here you would make it, for example, a distinction between z is 0, sorry, and z strictly larger than 0. So in this way you can try to construct different cases and treat them differently. Okay. In this recording, we're only going to do one of these different cases, namely this one. And we're going to look at the case where alpha is strictly smaller than 1, like I said before. So what do we do now? We're going to look at a sequence. So we're going to look at a sequence like this, right? And we want this to converge to 0, 0, 0 alpha. And all these numbers have to be between 0 and 1. Why is the, yeah, so I didn't really say that, but of course what you want is that the sequence is completely mixed. So that means that these numbers have to be strictly positive. But of course you also need that the other probability is strictly positive, which means this over here, right? So that's why these numbers have to be strictly between 0 and 1. So I'm not writing these, but they are there. And that is where this comes from. So you want all these numbers to be between 0 and 1. And like I said on the previous slide, we can try to achieve this by choosing alpha k identical to alpha. The question is, can we choose the other ones in such a way that that is actually true? Because like before, so these actually determine that one. So it's also clear that you can do that. But what we're going to do is to try to do that and see what is the condition on pk, qk, and zk for that to happen. So maybe this is a good moment to go back to the game tree. I don't need all the information from the game tree. Specifically, what I do not need is the payoffs for the moment. So what we have now is, what we want to construct is a probability pk over here. So 1 minus pk over here, and qk over here, and 1 minus qk over here. And yeah, so there's also a zk over here, but that will not be really very irrelevant for the moment, because the only thing that determines the alpha k over here is, of course, the probability over here and the probability over there. So we're going to apply Bayes' rule, and if we want to keep the alpha k equal to alpha, like we stated over here, then what does that mean? It means that alpha has to be equal to, well, the conditional probability is given by Bayes' rule. So what is the probability to be in this node on the left-hand side? Let me make that a different color. So the probability to be over here is, as before, 2/3 times, well, in this case, pk. And what is the probability of being in that information set? Well, it is this one, probability from the left node, plus the probability for the node on the right-hand side, which is 1/3 qk. And what is this saying? This is saying that alpha has to be equal to 2pk divided by 2pk plus qk. Which is saying that, so if you multiply by the denominator here, and you expand and you move things to the left and to the right, then what you get is that alpha times qk has to be equal to 2 minus 2 times alpha times pk. So you see what happens now is that fixing the alpha to a fixed probability, to a constant, induces a relationship between how we choose pk and qk. That means that we can choose one of them, and then the other one is determined by this expression. So that simply means that we have 1 degree of freedom less. We choose pk, and then qk is simply given by this formula. So that makes it, in some sense, easier. So this is the calculation that we did just now. And yeah, can you actually do that? Well, the answer is, of course, yes. Well, of course, well, maybe not, but of course, but you can, yeah, it is possible. And yeah, so you might think, okay, so how do we do this? Well, there's an easy trick, because it says that you have to have that this is equal to that. And what is an easy way to achieve this? Well, one way to do that is one way to at least have this equality is by choosing qk equal to this and pk equal to that. So by these choices, at least we have this equality, right? By yeah, that's very obvious. However, there's one problem. These are now constant sequences, and in particular, they do not converge to zero, what they are supposed to do, right? So the assumption is that the pk converges to that number, which is zero, and the qk's converge to that number, which is also zero, and that does not happen. But that's easily fixed, because you can simply divide everything by k. And because the alpha is strictly between 0 and 1, you can see that now the pk is also strictly between 0 and 1. At least if k is 1 or larger equal to 1. And I guess the same is valid for, well, so the qk is not yet, so of course, certainly strictly larger than 0. It may not yet be smaller than 1, because if alpha is very close to 0, then this is, and k is 1, then it's almost 2. But of course, it is true as long as k is at least 2. So you see, you have to choose the sequence. A bit careful, maybe you don't start at k is 1, but at k is 2. Another way to achieve this is to add 1. So there are many ways, of course, you can choose this sequence. Usually, if it's possible, there are millions and millions of ways to choose the sequences. So it's not that there's only one unique way to do that. Okay, so you could also, you know, put squares around it or whatever, and that would also still work. But of course, we want these sequences to be as simple as possible. So this would do the trick. A short remark about the Z case. I already said it doesn't matter much. So the only thing that you need to do basically now is to have it converge to 0. So basically ZK, you can choose any sequence that converges to 0. So, for example, 1 over k or 1 over k squared, whatever you wish. Good. So, and I think that is also what is stated over here. Yeah. And sequential rationality is something that we would have to check officially, but because we started with a perfect Bayesian equilibrium, we already know that this profile, this assessment satisfies sequential rationality, so we don't need to check it a second time. I think that is it for this recording. So the other PBEs, you can check them in similar ways. We will talk in more detail about this during the first tutorial on Tuesday, and also you can read a bit more information on how to choose these sequences in the reader. So have a look at that, and see you either on Tuesday or on next week in the next recording.